Professor Paolo Antonelli.
Thanks for the professor.
Who will speak on analysis of finite energy weak solutions for a class of systems in quantum hydrodynamics.
Okay, thanks for the introduction, and I would also like to thank the organizers for having invited me here, and especially for having organized this wonderful conference, because I really learned a lot, and it opened a new world to me. So as you can see from the title, I will talk about some systems in quantum hydrodynamics. This is, I want to present you some new results, actually. This dates back to my PhD work and some just further work afterwards. But since I'm coming back to those topics in research, so I would like to present you some things, and also maybe I hope this will be related somehow to the to the conference, and let's see. So basically what I want to study is a kind of system like the following one. How does this work? Yes. Like this one. So it's basically a compressible fluid, but okay, we will be back. It's in the whole space. I will take just positive time for some reasons you will see afterwards, but here, I can take the positive and negative times. I'm considering the Cauchy problem for this system. The system is Hamiltonian with this energy, which is conserved along the flow of solutions. And what I forgot to write here is that, of course, let's say the internal energy, or F, is related to P through the relation that P equals rho F prime of rho minus F of rho. And I want to, so let's say, in this talk I want to show you just some theorems proving global existence of finite energy weak solutions for some systems similar to this one. So this is just to warn you. It's just mathematics. Sorry, no simulations, no. I didn't save the world by discovering new physical things, and it's just analysis. So, yeah. Yeah, I will. Okay. So basically, rho is, let's say, at the moment, it's just a mass density of something. J is the current density. P clearly is the pressure. So if you basically erase this thing here, you get basically the Euler-Poisson system. So it's a compressible fluid with an electrostatic potential. And here you have a strange term, but I will go back to this later on. Anyway, let's say that for the moment, you just consider rho as a mass density of something, so a fluid, a quantum fluid actually, and J to be its current density. But yeah, I will go back. I just want to motivate, let's say, this system. So, what is it used for? It's used to describe, let's say, a number of physical phenomena as superfluidity, superconductivity. So you are the experts of superconductivity. Of course, I just mentioned here Feynman because there's this very nice paper about Feynman which relates the phenomena of superconductivity and superfluidity. Of course, it's a model for Bose-Einstein condensation. It's, let's say, it's more used sometimes than the Gross-Pidayeski because it's numerically more efficient. You don't have waves, and of course, I mean, it's also some similar systems are used to model also semiconductor devices at nanoscales. So quantum gases have particular features. So the first one is that the fluid is frictionless. So there is there is this wonderful video on YouTube, which is basically a documentary for BBC of an old documentary for BBC, I think from the 60s or something, which explains all the characteristics of superfluids, and you would see really like the superfluid climbing up the wall of the container and leaking down. It's amazing. So really, you have this fluid which doesn't have any friction. Another important feature is that, well, I mean, because it's okay, so maybe I was just too much amazed by the video. And anyway, so the another feature is you have quantum tunneling. So let's say the particles can pass through high barriers, and of course you have quantized vortices, which is important, especially in respect of this conference, right? So it means that you have vortices for which the circulation is quantized. It's an integer multiple of circulation quantum, which is like 2 pi over h bar, or h bar over m something. And so you see that's. I took I captured, this picture from the video. So now I don't know, but I really saw the superfluid leaking, and there was the fluid climbing up the wall and then going down. And here you can see, for example, some numerical simulations for the dynamics of superfluid vortices. I took this picture from Natasha Berloff's group in Cambridge, and here, which is really nice in my opinion, here you see basically some dynamics of vortices in 3D or superfluid vortices, and if you see, they really look like classical vortices for incompressible fluid. I mean, what is amazing is that there really is a remarkable analogy between superfluid vorticity and classical vorticity with high Reynolds numbers. Okay, so let's go back to the system. So as I already said, basically, this system looks like the compressible Euler system plus something, which is called the quantum Bombs potential. So this is considered as a potential. And let's say I will keep h bar just to emphasize the quantum nature of this potential. And so as I said, that's the energy. Here you see this is, let's say, the term which, let's say, gives this potential. And you see, the bomb potential actually can be written in different ways. For example, it can be written in this particular way, or this. And here, actually, you see, being a divergence of something, you could also interpret it as a quantum correction to the stress tensor. But I would rather stick to the second way, because I like it more and because it will be more handy for the kind of study I want to perform, let's say. So if you just please remember this formula. And I added this slide after Andres' talk, actually. Andres' wonderful talk. And why? Because Andres was showing those droplets which were moving on water, and he said that they had something related to quantum mechanics. It could be something related to capillarity effects of the fluids. Well, you see, I mean, there's a whole theory of compressible fluids with capillarity effects, which is described by such systems where K is the Korteweg stress tensor, which is written in this way. So this is basically a model for capillary fluids in diffuse interfaces. And actually here, you see that if you take a particular choice of the capillarity coefficients, then you end up with the QHD system before. So actually, you can also consider this quantum fluid as a particular capillary fluid for a particular choice of the capillarity coefficient. So I just mentioned this paper because in this paper by Benzoni-Gavache, Danchon, and Decombe, they study, let's say, the Cauchy problem for this system, where they prove some local existence for regular initial data. But of course, I mean, there's quite extensive literature on such systems. Okay, so let's go back to the QHD, and let's see its analogy with nonlinear Schrödinger equation. So you've already seen such analogy from Professor Betuel's talk, where he considered different, let's say, nonlinearities and a different space of energy, of course, because the Gross-Pidayeski equation has a non-trivial condition at infinity, but it's basically the same. If you consider a nonlinear Schrödinger equation of this kind, and you do what I call the WKB ansatz. So you say, okay, let's write psi as its modulus square root of rho times e to the I phase, which I will scale with h bar. Then, if I put this ansatz into the equation, I can see that rho and s satisfy this system. So rho satisfies a continuity equation, s satisfies something which looks like a Hamilton-Jacobi equation, plus this weird term here. And you see now that if you compute the gradient of u of s, which is a velocity, then you get something like the Euler equation. And so exactly for J, which is rho times u, so which is rho grad s, you end up by having basically a solution of the QHD. So rho and J solve the QHD system. And of course, I mean, you also have that the two energies are equal, because of course, I mean, if you put the WKB ansatz into this term here in the energy, then you get exactly the kinetic energy for the QHD. So what's the problem for WKB? Well, first of all, it's vacuum, as Professor Betuel also remarked. This is only valid as long as psi is different from 0, because in the vacuum regions, you cannot define S. Plus, so as I told you, I want to deal with finite energy solutions. So no regularity, just, let's say, psi in H1. So in this sense, the set where the wave function psi vanishes could be something terrible. And then, of course, I mean, I would like, let's say, to deal with vortices. And of course, I mean, if I take the WKB ansatz, so I have to assume psi different from 0, and then U is just a gradient, so it's irrotational, and then I can't have vortices, because of course, I mean, so you know better than me, vortices are exactly in the nodal region of the wave function, so where psi vanishes. So what we can do, we can compute the moments associated to the wave function. So just a remark. Let's say I call this Madelung transformation, but I think it's quite wrong, because the Madelung transformation should be, let's say, more what I call WKB ansatz, maybe. But let's say, let's take a psi solution of a nonlinear Schrödinger equation, and let's compute the moments. I have psi, it's the first moment related to, it's rho, it's the first moment related to psi, it's mass density or charge density. I compute its time derivative, I use the NLS equation, blah, 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 I get, yeah, surprise, surprise, the continuity equation. So, with current density here, which is defined by this. So it's h bar, the imaginary part of psi bar gradient of psi. So now I perform the same thing. I take J, I differentiate it in time. What I get, just with some algebra, is this. dt of J plus blah, 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 h bar squared, the divergence of this quadratic term, plus the gradient of the pressure. I have the electrostatic potential. I have this third order term. So you see, this almost look like the second equation in the QHD system, almost, because in the QHD system I had this divergence of J cross J over rho. I had the bomb potential in this way, but the bomb potential could also be written in this way. So you see, here, what's lacking, let's say, is that I should be how this blue term is related to the red terms here. And what I can do formally is, well, I have this. I just multiply and divide by rho. I multiply and divide by rho. I took this rho out, and I just say, okay, the real part of blah, 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 it's just a real part times real part minus imaginary. So it's just algebra this, okay, this. Now here, the real part of psi bar gradient of psi, it's exactly the gradient of rho half. This is exactly what I call J. So I have this, which means that by dividing by rho, I get exactly this. Okay, fine. We're almost there. The only problem is that I still divided by rho, which I didn't want to do because I want to consider vacuum regions. So how can we overcome this problem? So let's say, so the WKB ansatz is okay, but rather than considering S, the phase, anyway, we can consider e to the is, which we will call the polar factor. Let's say, so basically, this is easy to see, no? Given any psi in H1 or whatever, I can take a polar factor, so some function in L infinity with L infinity norm such that psi equals phi times the modulus of psi almost everywhere in R3. So, I mean, this is a kind of rough definition because, of course, I mean, you have that this phi is uniquely defined only square root of rho dx almost everywhere. But anyway, we will see it has the nice properties, actually. So basically, rather than considering S, so the phase in the WKB ansatz, I will consider phi, this polar factor associated to psi. And for this polar factor, I have this nice lemma, which explains you the nice properties about this. So given a polar factor of psi, so such that it satisfies those things, then of course, I mean, it's easy to see that the gradient of square root of rho equals the real part of phi bar gradient of psi almost everywhere. Now, if I define lambda to be h bar, the imaginary part of phi bar gradient of psi, then I have this, let's say, bilinear identity here. And furthermore, this decomposition is stable in H1 in the sense that if I take a sequence Psi-n in H1 such that Psi-n converges strongly to Psi in H1, then let's say the related hydrodynamical quantities converge strongly. So what is nice about this lemma here? First of all, well, basically, this lambda here, you should think of like j over square root of rho, because if lambda is h bar, the imaginary part of phi of psi, you see, if you multiply this by square root of rho, then here you have modulus of psi, you get exactly psi bar gradient of psi, and you have j. Then, what else I wanted to say? So what I couldn't do, let's say, what I couldn't do here, let's say, by dividing and multiplying by rho, can be done in this way for the bilinear term. So I have h bar, the real part of, let's say, the gradient of psi bar cross the gradient of psi, and I say, okay, I put phi bar and phi here, which, so you know that phi has modulus 1 square root of rho dx, so, and then I just have this identity, and this is furthermore stable in H1. So this is also quite nice because you see, I mean, the definition of the polar factor phi is quite poor actually, because phi it was just something such that psi was phi times its modulus. So, well, nothing. And actually, so if you have, let's say, psi converging strongly to psi in H1, what you could have for the polar factors, let's say, it's just up to subsequences, always. Up to subsequences, it's just a weak star convergence in L infinity. And so, if you would consider, let's say, those quantities real part of imaginary parts of those guys here, you would say, okay, so this just converges weakly because strong times weak. But actually, you can improve this convergence to the strong convergence. And this is really, really nice in my opinion. So, actually, through this, so I can, let's say, I can relate. Didn't I use this before? Okay. So I can so you see, I can relate now this bilinear term here with those two red terms. And so basically, now it's nice because I can find a weak solution to the QHD system. So let's be precise. So let's see what is a weak solution for me. Finite energy weak solution. So for me, finite energy weak solution then means that basically there exists two functions, square root of rho lambda, such that square root of rho, so this function is L2 log, H1 log, lambda is L2 log, L2 log, and through these functions, I define rho and j in this way, and rho and j satisfy, let's say, the QHD system in the weak sense here. Plus, they satisfy this generalized irrotationality condition. So for almost every t and x, I have that the curl of j equals twice the gradient of square root of rho wedge lambda. So what is that actually? I mean, this is something. So imagine that you are in the regular case. So that basically you are maybe WKB. You can write. You can define the velocity fields u. You can differentiate how many times you want and so on. Basically, what tells you this in a regular case is that basically the velocity u is irrotational in rho dx. So this is basically what should be equivalent to this expression in the regular case. So it's let's say the kind of the right framework. So u is irrotational, but in the place in the points or whatever where rho vanishes. Of course, I mean this whole this thing holds true only the regular case, but we can let's say we can say this for almost every t and x when we consider just finite energy solutions, because basically these are two objects in L1. Okay, so in this way, I can say, okay, I take C0 in H1, and if I define rho 0 to be the mass density related to C0, J0 to be the current density related to C0, then there exists a global finite energy weak solution to the QHD system with those initial data, and the energy is conserved. Okay, so this is just an easy consequence now to what I said before, because I just consider C0 and I consider the NLS equation I wrote before. For the NLS equation, you really have all the nice theories that you want with all the nice properties and estimates, blah, blah, blah. So I know that there exists, in particular, a global solution, psi, continuous for all times, with values in H1. So with this psi, I can define square root of rho and lambda by means of the polar factorization, basically. And by using polar factorization, maybe just some density arguments, the usual stuff. So by using this, I just know that now square root of rho and lambda defines a finite energy weak solution of the QHD system I showed you at the beginning. So just some remark. So let's say the only problem here is that I have to start from a wave function. I can't say, okay, for any ρ0, J0 in some space, I can find a weak solution. So the only constraint is that the initial data are related to a prescribed wave function in H1. Okay, this could be anyway, let's say, kind of acceptable in a sense, because I'm trying to study some quantum systems, so maybe there should be some wave function, but it's just an excuse, let's say, because anyway, I'm not considering all initial data I could. But the next thing is that I don't require any further regularity on the initial data, neither smallness or especially boundedness away from zero. So I can have vacuum regions for the wave function, which is nice because let's say that I could allow vortices in this theory. So far so good, let's say. Now really the main thing about our work was actually to study this system here, where now you have an extra term here, J, which is a dissipative term. So you see, it's a relaxation term. And so this system was studied quite extensively in the community of modeling of semiconductor devices. Because this J was a relaxation term which models the collisions between electrons in the semiconductor. But this was just derived phenomenologically, actually, by those guys here, Bleu, Tequier, Baccarani, Wortmann. And then actually there was, let's say, a derivation by Gardner, just by considering, let's say, by considering a quantum Boltzmann equation and then taking the moments and trying to close the moment somehow. You see here, the energy anyway is the same, but it dissipates along the flow, and this is, let's say, the dissipation rate for the solution. And so you see here, okay, so this is the theorem I want to prove, let's say. That's basically that's as before. That given any psi in H1, I can define a ρ0 and a J0 in the same way, and then I have basically a global finite energy weak solution because I have it for any t from 0 to infinity. So I have a global finite energy weak solution, ρ and J, to the QHD system with collisions, and the solution satisfies this property here. So, okay, we will go back to those properties later. But anyway, you see here, basically, because of this term, which introduces a dissipation, actually, the analogy with the NLS equation is destroyed, basically. So, because actually, what we should study, let's say, in the wave function description is an NLS like this, with this extra term here, which is not well understood. I've never, to my knowledge, there's no, let's say, Cauchy theory for this kind of equation, because basically, yeah, this is well defined, but you see, this is a nonlinearity which may have jumps or may behave not really well. This is the argument of a complex number. I mean, it's not really a nice equation. So let's say to study this and then to just apply the modulum transformation to recover a weak finite energy weak solution to the QHD system with collisions would be a bit complicated. Actually, I mentioned those results because, for example, in this paper by Jungel, Mariani, and Rial, they study local existence for the system basically by looking at the WKB formulation of this equation here. But of course, I mean, they have to start with psi, which is uniformly bounded away from 0, which is regular enough, and then of course, I mean, the result is local in the sense that they stop, let's say, the local existence time before the vacuum appears. So, and here in this other paper, they use more, let's say, hyperbolic systems of conservation laws techniques to study the system, they symmetrize and so on. But anyway, there's this local existence result with regular initial data, and what they can say here is that you have global existence just if you start close to a subsonic stationary state of the system. Okay, so our approach was to use the fractional step, basically. So we can so you see the parts, let's say, with the collisionless part, it's easy, in the sense that okay, you have the NLS equation, you do the modulum transforms, and you get a finite energy weak solution of the collisionless QHD. Then you have to update with collision. So we say, okay, at each time, at each space-time slab with tau, we solve the NLS equation, which is basically the QHD without collisions, and then we update here at the end of each slab with collisions. So what does it mean? It means that basically at the end of each slab, what remains to be solved, it's basically just an ODE, which is this, which again approximates to the first order because, I mean, I just want to find a weak solution. It's okay. So what would it mean? What would this mean in the WKB setup, let's say? In the WKB setup, this would mean that we just have to change the phase. We have to update the phase in this way. So, I mean, so in the updating, I have that rho nu remains constant. J nu has to be updated, let's say, in this way. So let's say that you are in the WKB, so J is basically rho grad S. So rho nu, S nu, it has to be 1 minus tau, rho old, which is rho nu as old. And then, so you see, we just have to change a bit the phase. The thing is that I don't want to play with WKB because I want to play with vacuum states. And so what I should do morally is to take the polar factor of psi old, so what I get, let's say, arriving from here to tau, I raise it to the power 1 minus tau, and I get this new wave function in this way. Of course, I mean, this is, I'm cheating, of course, because I told you that phi has modulus 1 square root of rho dx almost everywhere. So maybe where square root of rho vanishes, this could be, I don't know, anyway, close to 0, whatever. So what is this? But here, of course, I can use, let's say, I can use the stability in H1 of the polar factorization, which is good. So what I should do, more exactly, it's not even this regularization by the H1 stability. It's even a bit more complicated, but this is just take this slide just as a technicality, because this is just to recover some estimates. I will explain you this, this slides later on. But basically what I do, so let's say in the updating, so at the end of each space-time slab is this. I take, let's say, the psi old, and I define psi nu such that I have that the two mass densities equal. The new lambda satisfies almost what I want to be satisfied, with just a small error, which is epsilon, which is arbitrary here. It's not related to anything, not even to tau or blah, blah, blah. And especially, I have this. So that's the gradient of Cn, let's say, can be expressed in terms of the gradient of C0 in this fashion. And this is actually important, and you will see later why. So basically, here phi star is just a kind of a polar factor, whatever function. And this is a term which is controlled. So basically what I do, I have this. Here I have R3. Here I have R plus. I divide R plus in many subintervals. So here I solve the NLS equation. So let's say that here I have, so I start with C0. I know that I have a solution. Let's call it psi tau. Psi tau now in, let's say, in 0, tau cross R3. So I know how, so, and it's continuous. So I know what is this thing here, basically. So I take the limit from below at time tau. With this, I can define with this lemma, basically, psi tau at time, let's say, let's call it tau plus, but at time, well, at time tau. No? With this, I can start again here with the NLS equation, and so on, and so on, and so on. So basically, for any fixed tau positive, I can find this function psi tau, which now lives, so I end up, for any tau positive, I have this psi tau now on the whole R plus cross R3. And let's say what I can do with this function here, right? So first of all, okay, I got this psi tau. I can construct, let's say, square root of rho tau lambda tau. Well, first of all, we should check that, let's say, the scheme for the approximate solutions is consistent. So first of all, we prove this, that if I have a strong limit of square root of rho tau, lambda tau, in L2 lock, H1 lock, L2 lock, L2 lock, then, and the square root of rho tau, lambda tau is the sequence of approximate solutions defined by basically by psi tau, then square root of rho and lambda, so their limits, solve the QHD system with collisions. Finite energy, blah, blah, blah. Weak solution. So, I mean, this is easy. You just assume this convergence. You plug, let's say, the construction of the approximate solution in the weak formulation, similar to the one I showed you. You play, it's easy, and you show that in the end, square root of rho and lambda solve the QHD system with collision. But now we do have to prove that they do converge strongly, otherwise. So we need some estimates on the approximate solutions. So the easy estimate is given by the energy. The energy is dissipated for the approximate solutions. What we have is not the exact, let's say, dissipation, but anyway, because of this strange updating procedure we have, actually. But anyway, we have this energy dissipation inequality for the approximate solutions. So this in particular means that the sequence psi tau is uniformly bounded in L infinity or plus with values in H1, which means that up to passing to subsequences, I have a weak limit for this. The problem with this is that I still have to play with quadratic terms here. I can't prove any convergence of this thing here if I just have this weak convergence. I could have some singular measures otherwise, and I get some troubles. So what I can use here actually is the dispersion. I mean, so the nice thing about the whole stuff is that I really rely on the nonlinear Schrödinger equation, so which has a number of nice features, especially all the dispersive estimates, which are this one, just to show you. In particular, I will use Strigat's estimates, and Strigat's estimates are dispersive estimates given for general dispersive equations. There's a wide literature about this. Let me just mention Strigat's, because of that was the first work. Ginevra and Velo, Kill and Tau, because they let's say they set up the whole range of possible estimates. And so basically what we have is this thing here, that basically the Schrödinger semigroup, because of its dispersive nature, it gains some integrability. So if you start L2, then okay, you see that a free Schrödinger semigroup gains some integrability in time with values LR in X, with Q and R, you see, are given by this algebraic relation here. It could be in this range. Also, analogously for the inhomogeneous part, for the GeoML part. And then we use the local smoothing estimates, which for Schrödinger equation are given by results by Constantin and So, Scholin and Vega. Where you see that's, of course, I mean, you're not dealing with a parabolic semigroup, but still locally in space, you're gaining half of derivative, which is a good thing. So what you can do with this bunch of estimates? Well, you write, so after having constructed, let's say, the sequence of approximate solutions, you write down the expression for the gradient of psi tau at time t. So if I may go back to this updating lemma, all this story and this bothering about writing psi in terms of psi holds through this expression here is exactly because I wanted this neat expression for the gradient of psi tau. Because, I mean, the problem is this one. The problem is, is that if I would define, let's say, psi nu as just phi to the power 1 minus tau times the modulus of psi holds, so that I have that rho n equals rho old and lambda n equals exactly 1 minus tau lambda old, then I would get a bunch of problems with the gradient of psi n, which is something like, I don't know, let's say a polar factor of phi tilde times the gradient of psi old plus blah, 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 blah. And then when I want to, let's say, when I want to see the expression for the gradient of psi tau, it's a mess because I would get some terms like this, let's say, t minus n tau. Let's n be and I would have this cross polar factor n, let's say, then just another bit of Schrödinger evolution. So u of whatever is just e to the I t Laplacian. So another bit of free evolution times another polar factor times another bit of, and so on and so on. And this is just the free part. Imagine the inhomogeneous part, it's just a mess. And now, I mean, here, what you would need was to compute basically the commutator between those things. But this is just an L infinity function, and you can't really use any good commutator estimates, which I know, at least. So in this, let's say, complicated, but I mean, way of updating the wave function, I get this more neat expression for the gradient of psi tau. And here, I can apply the Swigat's estimates. You just, it's standard. You use some bootstrap argument, and you get some, you gain some integrability for the gradient of psi tau. So you know that the gradient of psi tau in those spaces is bounded by something which depends just on the initial energy, initial mass, and the time. By using those new a priori estimates, you can also use the local smoothing and say that basically, yeah, you're locally in space, you're more regular. And now it's fine, actually. Because with this estimate, you just apply an Aubin-Lyon's type lemma. What we use here in particular is a result by Rakotosom and Temam, if I'm not wrong. And you say, yeah, well, you see, actually the gradient of psi tau converges, the sequence gradient of psi tau up to subsequences, blah, 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 converges strongly to the gradient of psi in L2 log for any finite t. So this can be translated in terms of the hydrodynamical quantities in this way. So now once I have this, I have the consistency proposition, which tells me that rho and j defined in this way is a finite energy weak solution to the QHD system with collision. So basically, in this way, I get this global finite energy weak solutions. And so I proved the theorem. So just let me go back to some remarks. So again, the initial data are given by some wave function. Again, you have no regularity, smallness, or boundedness away from 0, but you see, but this was also true actually for the collisionless thing, that you don't have uniqueness, of course. I mean, you construct a particular solution. You don't know if this solution is unique for the QHD system. Actually, we are trying to work in this direction too. And, and then actually, this is important. If you remember, let's say the wave function description, which would be analog to the QHD with collisions, was a bit, well, I mean, was a bit not well defined, I think, because that nonlinearity is anyway not good. And actually, in this way, actually, you can't say that the limiting wave function psi solve any nonlinear Schrödinger equation, actually. So you end up with some psi which you don't know what it is, but their, let's say, hydrodynamic moments do solve the QHD with collisions. So let's say variations on the theme. What happens if you put some? What happens if you put some electromagnetic fields here? This is important because it's let's say the quantum version of MHD, and actually it is studied by some physicists to study quantum plasmas and interaction between ion and acoustic waves. So basically, what you would study is just let's say the QHD with so quantum bond potential plus electromagnetic forces given by the Maxwell's equation. And so this is, let's say, in the wave function description, this is related to the Maxwell-Schrödinger system. Let's say I'll just consider the Coulomb gauge because it's better. And in the Coulomb gauge, the Maxwell-Schrödinger system is written in this way. And if I take rho to be, again, the mass density related to psi and j to be the current density, where here, now you know better than me, but you have the covariant derivative. And then basically you could say, okay, if rho and j are those quantities here, well, then and if, okay, psi and phi a are a solution to the Maxwell-Schrödinger system, then rho j E and B defines in this way, and E and B defined in the usual way through A and phi, then are a solution to the QMHD. So the thing is that actually this is kind of just applying the polar factorization before and applying those results, of course, I mean, those existence results for the Maxwell-Schrödinger system. Otherwise, I wouldn't know what to do. Well, actually, this is psychological terrorism, but you see, this is interesting, actually, to study the bipolar charged fluid. So with ions and electrons, and when you consider two fluids, then you have some momentum exchange between the two fluids. And you see, they really look like the collision term we considered before, actually. So let's say first step would be to consider this thing here, and maybe to apply, let's say, the fractional step argument. Problem is that for the Maxwell-Schrödinger system, we don't have quite clear Strigatz estimates, for example. We don't have quite clear dispersive estimates. And well, the problem is that this Maxwell-Schrödinger system is highly coupled, and you can also have standard traveling waves, actually. So It's difficult. The idea would be, let's say, to use a regularized version of the Maxwell-Schrödinger system, as in the paper by Guo, Nakamitsu, and Strauss. And then, let's say, recover the hydrodynamics and pass to the limit and so on. So let me just finish by giving you the references for the QHD system. And I think I will stop here because I'm already late. So that's, those are the things we done some time ago. And now we are trying to go back to this. Okay, thank you very much.
Thank you.